Okay, so let's continue with the next lecture, that is image histograms, which is one of the most basic operations that you can do in images. It is the first one that you will see during the course. So, an image histogram is simply counting how many times we have seen a particular gray value or a particular intensity value in one of the channels. So, for instance, here we have this image, and we said last time that images, especially monochromatic images, so gray scale images, they go from 0 to 255 with a single value. So we don't have three values, one for each one of the channels, but we have a single value, and it is the same value for the three channels. Okay, so if we count, so it goes from 0 to 255. We count how many times we see 0, how many times we see 1, how many times we see 2, and all the way to 255. So this is the result. So we have seen 3 million times a value close to 20. And let's remind that 0 values are dark values, so 0 actually is black, 55 is completely white, and then you have all the grayscale here. So this image is pretty dark, and that is why most of the pixels are here, around 20, 30, something like that. Okay, what about this image? This image is much brighter than the one before. So now we should have more counts here. So not more counts. The number of counts is the number of pixels, but we should have higher intensities. And these higher intensities, now the histogram looks a bit different. Now we have two bumps in the histogram. Before we only had one, because most of it was dark. But now this tells us that here we have two different kind of regions. One that is darker and another one that is brighter. So actually the darker one is this, so the soil and the trees, and the brighter one is the sky. And something else that we see in this histogram is that there is no pixel with value 0, no one with value 1, up to value 75 or something like that. So all these values, they have not been used, and all the values from 180 onward, they have not been used either. Okay, so then let's look at this one. So now we are using most of the dynamic range. The whole intensity is called, the whole axis is called the dynamic range. So we are using most of it. There is a region that we are not using, so very, very dark pixels we are not using. But then there is something new, that is this spike here. So this spike is, we are saturating at 255. So somehow the intensity counts how many photons are coming to the detector, and you have to calibrate your detector so that there is some kind of response like this. So this is number of photons, detectors, and this is the intensity, the value that we will read. And typically they behave something like this. So there is a region in which it behaves in a linear way, but beyond some point, it saturates and all the time returns the same value. And it is the same down here, below a number of photons. So some number, this is not 0, 0 is here. So below a given number of photons, it doesn't return anything. So we have saturated, we are receiving more photons than we can encode, and then we have this spike. So there are some regions here that are whiter than we are able to record. Okay, now we have color images. Yeah, you have a question.
About the before, the one you drew. No, the one you drew, the default.
Okay. This one.
Yeah, in case we had a high number of range, you might like. Oh, sorry, never mind. Yeah, I just realized something. I wanted to ask you.
You mean this number here?
Yeah. I wanted to know if having a high range does also mean having a higher number of photons you can have.
Not necessarily. Not necessarily. So this is one thing, and the other thing is how much you encode. So how many steps you have here. So if you're used to 255, you have 256 steps, but you may have them even smaller. So 2 steps, this, and then your maximum number is 635, something like that. This is 5, I think. This is 5. So this is the maximum number, but still, in terms of number of photos, you have the same, only that you are encoding it with different. So actually, this is a 16-bit encoding, and this is an 8-bit encoding. So one thing is what is your input, and something else is what is your output. So the output refers to how many steps, and the input has to do with the hardware of the detector. And okay, so yeah, the number of outputs, the number of bits also has to do with the hardware. At the end, everything is hardware. Right? Okay, so here we are. So now we have color images. So for a color image, now we have 3 channels that with different values. So we can calculate the histogram, the 3 of them. So we compute the blue histogram, so the histogram of the numbers in the blue channel, in the green channel, and the red channel. And then we already recognize some of the features we already know. So for instance, there is a saturation in red. So the camera here could not record pixels beyond this number of red photons now. And then the big bumps here, so in the green and blue channels, they correspond. Do you think they correspond to the sky? So this big bump here, blue one, can it be the sky? Seems so, no? It's not, of course. The sky is relatively bright, so it has to be this one. So this one is all this area for which you don't need any blue. It's almost red. So you don't need any blue, and then you have very low values in the blue channel, and the same for the green. Okay, then for instance, this image has mostly green. So mostly green means if you look at the tails, the green tail is much thicker than the other 2 tails, meaning that you need more green values of high intensity than for the other 2. And we already recognize this pattern of I don't need any blue here, or very little blue, and then most of my blue values are very low. Okay, and another one with saturation here also. So there are some regions that are much darker in terms of blue than I can record, and they are saturated now on 0. And it is actually saturated on both 0 and 255. Yeah, so it is all the time the same idea. Okay, very good. Then a histogram is simply counting. So it is the histogram for a gray image, and the value G is the number of pixels. So this is the cardinality of a set. And this set is all those pixels such that the gray value at that location is this value. Okay, so that is the way to read that. And then if it is a, this is counting, so it is counting, it is a function. If it is a function, it must have some domain and some range. So the domain is the values here, they can go from 0 to 255. So this is my domain. And the range is what is the actual count. So the actual count can be 0. And the maximum count that I can have is the number of rows, number of columns. So let's say that my image is flat. All the pixels have the same value. Then the count for that gray value is as times C. Okay. Any question to be? This is very easy actually. And yeah, so this is something of MATLAB that MATLAB starts counting. So it stores things. The first index is 1, not 0, and then so he's saying from 1 to 256 it corresponds to G minus 1. But this is something of MATLAB. So in general, you should take this idea. So it is for counting how many times I have seen a particular value, and let's forget about how to store that thing. Okay, so there are more examples. So let's say that we are given this image. This is the histogram. And now let's try to do a very interesting experiment. Okay, so we are given this image. And this 24-bit two-color image, you already know what it is, that we have 3 channels, red, green, and blue, and each one of them has 1 byte. So in total, we have 24 bits. And that configuration is called true color. But now we turn it into a 16-bit, a 4-bit image that can only take 16 different values from 0 to 15. And this is how it looks like with 4 bits. And now we can do the following. We can draw a mask with the image with particular values of interest. Okay, so let's say G equals 15. So G equals 15, so those are the brightest points. The brightest points here are these white points. And we see that those are the regions, the points that have been highlighted there. So the highlight is here is black, but the points are white. Okay, but so again, this appeared the other day. One thing is the information, the other thing is how to display that information. So the information is white points, but the way to display, they have chosen to put it black. Okay, then 40 values or whatever, I don't know. These very dark values. So G equals 0 is very dark. So the darkest points are this one. So for every gray value, you have an activation pattern. So this is the activation pattern for G equals 0. This is the activation pattern for G equals 15, and all the numbers in between. And then you count simply how many pixels are active in that pattern. That is the histogram. Now, it is an interesting way of thinking of images. So it is like an overlay of 60. If you have 16 levels, it is an overlay of 16 masks, each one with some active pixels. And then you simply count, and then this is our histogram. Okay, so the height of these bars should be the numbers of pixels in each one of the masks. Okay, what if we have a color image? So we have seen how to compute the histogram for gray images. So all you have to do is to apply it in the 3 channels. So you compute the red histogram, the green one, the blue one. Something very easy. So this is our 3 histograms, and then you can do also something else, that is you can turn your image into a gray value image. So like black and white as we did here. So this was a color image, but you can compute something that is black and white, like this one. And then you can compute the histogram of that gray value image, and that gray value image is called here luminance. And we see that the histogram of the luminance is not the average of the other histograms. And we will discuss more about that later. So it is not the average, it is kind of similar, but it is not exactly the average of the three. But somehow they resemble, so they have more or less the same kind of shape. Okay, so we will define luminance later, but let's define first something very easy, that is the value. The value of an image is, okay, so I want to convert this color image into gray. So one possibility is just to compute the average of the red, green, and blue channels at every point. So the value at a given point is the red, green, and blue channels at that point, and then I compute the average. So that would be a very easy way to convert a color image into a value image. And this is the luminance. Okay, so why 1/3? 1/3 because okay, it seems to be natural, but many years ago, so in the 50s, they were doing some 53 actually. In the 50s, they were doing some experiments. It was a time at which television went from gray, black and white television to color television. And then they had, so they were broadcasting the color images, but there were still many black and white television. So they had to turn the color information into a black and white information that they could display in the televisions that were already existing. And then they started to think, okay, so why 1/3, 1/3, 1/3 could be any number. So which are the nicest numbers? And then they did a lot of experiments with people. Then when do you think this gray image is the best? And they came out with these numbers. And these numbers tell us actually something very interesting. So the green channel was more important, the red channel was the second most, and the blue one was the last, the least important. And that tells, why do you think it is that? Why green is more important?
Because of the roads in the eye.
Because of the
Road cells in the eye.
vote.
Roads.
The roads. Yeah. But why the rods actually? Yeah, rods are green and red. So, but why the rods evolved to see green?
Takes the green color.
Yeah, but why we have more green rods?
Because it's the green tells us the profundidad.
Has to do with that, but because of our environment. If you think of the evolution of man, we were raised in the forest, and in the forest, most of the thing is green, and we have you want to compute the depth. So for depth, we need the two eyes. Not with only one eye, you cannot compute depth. But you need the two eyes, and also you need very precise eyes in the green channel. That is most of the things that you see. And actually, the blue, by night, we cannot see too much. So it is related to our lead sensitivity to blue. Okay, so yeah, and these computationally, what is interesting is that, okay, you can convert a color image into a gray image using some weighted average of the different channels. Can be this thing, but could be almost anything. Not almost anything. The quality would be different, but you can put in general any number there. Okay, good. This is how to compute that in MATLAB. Okay. So we have now the two images, the color image and the value image. And here we have the histogram of the value. Okay. Now we know how to interpret that. Here we have the histogram of the luminance. If you look at the histogram, it changed a little bit. So they are not exactly the same. When the images themselves, they are not exactly the same, but not so different either. Okay, then we can try to compare the RGB and B, so red, green, blue, and value histograms. So these are the ones, okay, whatever they are. And with the average, so we compare here the value histogram with the average of the RGB histograms. So the average, you take this red, green, and blue curves, you compute the average, this is what you get, the blue one. And the value histogram is the black one. So you see that they are quite different. And that points to something. That is, it is not, the value is an average. So what it is saying is that the histogram of the average is not the average of the histograms. So let's put it like this. So you have some input image. Then you have the average. Then you have histogram. And on the other possibility, first you compute the histogram, and then the average. And they are not the same. So in general, when two systems can be interchanged, so when so here we have the output of HG, and here we have the output of GH. When is it that IHPA is equal to I?
LTI,
Sorry?
LTI systems.
In LTI systems, yeah. In linear time invariant systems. So linearity means linearity means two things. One is that let's say that I will call it the inputs and outputs. I will call them X and Y. Okay? And so let's say that X of R, this is an image, goes into the system and it produces Y of R. I only write it for one of them. The other one is the same. Okay, so a system is linear if A sub produces A, Y, G, and X1 5 X2 of 1 produces Y, G1, Y, G2. Okay, so that is linearity. What about time invariance? Time invariance means that if I shift the image, what I get is the shifted response. So if my input is X of R minus R, no? And the output will be I of R minus R. Okay, so two systems commute if they are both LTI. Here T was time, so linear and time invariant. So here with images, it is a space invariant. So not time invariant, but a space invariant. Okay, so the average, computing an average, is it the linear system? Is it the linear system, computing an average? Yes, it is, no? So this is linear, but it is a LTI, so this one is LTI. What about the histogram? The histogram is a linear transformation or not? No. Why not? Let's see. Okay, so let's say I have two images. I have one, another one. So this is full of zeros everywhere. This is full of ones everywhere. And then you compute the histogram. So this histogram here, second, call it H1 D. So it is this histogram, it is full of zeros, so it will be a delta there. What about this one? It will be now H2D, and then it will be a delta here. Let's say 255. Okay, so to make it even more pronounced. So this will be at 255. Okay, so this is the histogram of this one. This is the histogram of that one. Now I compute a new image that will be I3 is 1 of y1 of 2. And this will be, so we have to round, it will be 128. So the histogram here, histogram will be here. Same height. Okay, so same height. So this is RC, this is RC, this is RC. Number of rows, number of columns, and this is 128. But so this is H3 of G. But let's make it red. 1/2 of H1 2 G. It is this thing. RC, which is not the same as that one. Okay. So computing a histogram is not a linear LTI. So this is not LTI. This is not LTI. So if something is not linear, then is it time invariant? Computing the histogram is time invariant. So if I shift my image, the number of counts, ignoring the borders, okay? The number of gray values will be the same. Yeah. So if I shift the image, the count doesn't change, but the linearity is not preserved. So it is not the same computing the average and then the histogram, or computing the histogram and then the average. Okay, good. So yeah, this is why these two curves are so different. Yeah. Okay, very good. Then, yeah, this is MATLAB code to compute these things. We don't care about MATLAB code. And then the last thing is the relationship between the histogram and the probability density functions. Okay, so I will explain it here. So the first thing is that it has already appeared. Has appeared somehow. So let's say this is a histogram of my gray values, and I have some function here. My function is always discrete, okay, but I'm lazy to draw all the bars, but it's a discrete one. Okay, so if I sum histogram for all gray values from b equals 0, 255. What should I get? Pixels, number of pixels. Okay, so this should be RC. And in general, I will call it the area of the image. Okay, very good. Then I will compute something that is called a probability density function. Let me say which letter they have used. Small p, I think. Yeah, small p. So we'll call it small p of G. And for the image I, this will be Hij divided by K. So it is simply a normalization. So if the, let's make this green, for instance. So let's say that this is I. So if I represent in the same plot with different scales, okay? I represent these two. Hi, it goes, I don't know, to 10 to the 6, as we saw before, because I have a million pixels. But Pij goes, you know, to 10 to the minus 4. Why? Because when I sum, if I compute this sum, if I compute the sum from G equals 0 or to 255 or I, what should it be? 1. So we 1 because it is 1 over A goes out and then the sum. So this is A divided by A. So this is 1. So this tells us that this is a probability density function. Probability density function. And the integral of that, or the sum of that, for PDF. So the integral of that, or the sum of that, has to be 1. And so it is the probability of what? It is the probability of taking a pixel at random. So I take a pixel at random, and the intensity of that pixel at random, let's call it smaller or equal G. So you have your image, you take at random one of the pixels. What is the probability? No, sorry, this is not a smaller or equal. That will come later. That will come later. So it is the probability that it takes the value G. Okay, so it is the probability taking a pixel and having a particular value. Okay, so then if this is a probability density function, I can compute the, let's use a different code for that. I can compute the CDF. CDF, I think they use capital P, so capital P G, with the sum from G prime equals 0 G of Pi right. So it is the probability of I being smaller than or equal. And this is called the cumulative density function. Okay, so now we can connect all the histograms that we have seen now to a branch of statistics. A branch of statistics, and actually that would be very important in some contexts. I think we will see one of them, but it is you take a pixel at random. What is the probability of having a particular value being smaller than the particular value? And then something more about this is, let's say that you're given PI, then you're given the PDF, you know how to compute the CDF. What about the opposite? If you are given the CDF, how can you compute the PDF? So this is can do it this way. So you can decompose this. Okay, this is the sun. Right. This is the sun. Okay. Sun from G prime 0 to G minus 1 of the P I G prime plus Pi of G. Do you agree with that? So this sum goes from 0 to G, so I go from 0 to G minus 1 and I add the last one. Okay, very good, but this is the P, capital P of G minus 1. So this is capital P G minus 1 plus Pi, the small one, G. So now you can solve for it for the small one. The small one is P G minus P I G minus 1. Okay, so this is, let's say, big ones. Yeah. So it is, so given the CDF, I can compute the PDF, and the opposite. Given the PDF, I can compute the CDF. Right? Okay, so then, yeah, this is, all these slides are exactly that. So, yeah, this division by the area is called the normalized histogram, and then this is the same I was explaining. So this is the CDF, this is the PDF. And then given the PDF, or given the CDF, how do I compute the PDF? And the opposite, given the CDF, how do I compute the PDF? And if you think that the image is a continuous image, so not discrete defining pixel, but defined on a continuous gray level, then the continuous gray level, you have to substitute summations by integrals. That's it. And the opposite, so the summation is an integral, and the opposite of the integral is the different the derivative. This is called the first difference, actually, that ratio.
In this case, or in the error case, do you use the value of the image or the luminance?
You can do it for whatever channel you want. You can do this for the red channel, for the green, for the value, for the luminance. You can do on whatever.
But for example, in that case, if you just tell us in broad sense, do you do of the gray level? Should we use the luminance?
Okay, so I don't care. So as long as you are consistent, so when you say, okay, for me, gray is the value, and then you reason about the value. For me, it is the luminance, and we will see actually more ways of converting it to gray values later when we study colors. Yeah, but as long as you are consistent and you know what you are saying, I don't care which one you use. More questions? So we have seen our lecture, and we will make a break now. And after the break, we will continue with the practice, and I will give you some time for doing some practice. Okay, very good.